before we go into any new things, I wanted to make a comment, and I think it was one of you, is it Jivi, who made this very, very good comment about flat out a mistake that I made last time. I have to teach there early in the morning, and I'm not very smart in the morning. But so I wanted to make a comment about that. So let me just go back to tensor products. Of K vector spaces and K algebras. Okay, and I made a comment about this in the forum. You should look at it. I wrote things pretty explicitly, but I want to also say it on film. It's extremely important when you talk about tensor products, whether you're taking the tensor product of vector spaces or of algebras. And in general, as you probably know already, when you're studying algebra and you have an object, you want to say what kind of object it is. Is it a ring? Is it a vector space? Is it a module? What is it? And I was not careful about that last time, and I made a mistake. Okay, so, and maybe I'll just say quickly that the first, maybe let's talk about the second example last time, where I wanted to show that these things are isomorphic as are algebras. Okay, and so let me say what I did and what I did not do. Okay, so what did we do? I said, well, first of all, I need a map. I need a map of isomorphism from here to here, and we have a nice trick to do it. Whenever you want to map from a tensor product to something, you you start with a bilinear map. Maybe I'll call this map F, where what we did is that we took a complex number lambda and a real polynomial p of x, and we mapped them to lambda p of x. Okay, this is bilinear. And so it descends. Okay, now, so it descends to a map to the tensor product, from the tensor product to this. Okay, and that is something that we proved, that we get a linear map. Okay, and so you know that a linear map is the same thing as a homomorphism of vector spaces. Okay, so linear map, this is a synonym of homomorphism of vector spaces. Okay? And we showed that this is bijective. Okay, and that we did carefully. And so that means that these things are isomorphic as vector spaces. And again, it's very important because when you say as vector spaces, you have to say over what field. And here we're considering everything as a vector space over the reals. Okay? But GB's comment is that this does not yet prove that this is an isomorphism of our algebras, because we need to show that this is a homomorphism of algebras as well, of K algebras, and so far we have not checked that. Okay? And so to check that, we need to check. So F bar is a homomorphism of K algebras. And to be a homomorphism of K algebras, we already have all the properties except the property that this should preserve multiplication. Okay. But what you'll see is that actually this is really very straightforward, because if you take, I don't know, let's take f bar of lambda tensor p of x, that's lambda p of x. And let's take f bar of mu tensor q of x, and that's mu q of x. And so, and now if we take f lambda of this times this, now again, it's important to realize that we are taking this and regarding it as an algebra that has a product, and the product is lambda mu times p of x q of x. Okay. So this is the product of these two things, and by definition this is lambda mu p of x q of x, which is this times this. Okay. And so now we have checked that this does respect the product, and therefore this is a homomorphism of K algebras, and because it's bijective, then it is an isomorphism. Okay. So again, the moral of the story: don't be sloppy. You have to be very careful when you prove that two things are isomorphic. You have to be careful about what, you know, the language for this is what category you're working with, right? And make sure that if we're asking for an isomorphism of R algebras, then you need to check it in the context of R algebras. Okay? And I wrote more about this in the forum. I didn't lie in the last class, but there were some things that I didn't say, and so in the forum I wrote everything explicitly that we missed. Okay. Does that make sense? Any questions about this? Okay. So let me just finish the review of tensor products by just giving you some useful facts. You can consider them useful facts, and you can also consider them instructive exercises that you should know how to do. Okay, so I'm not going to solve them, but if you see that you don't know how to prove one of these things, then you should try it, and I'm happy to help you. So one, this is very important, and this you have to do in the homework, that if you have basis for two vector spaces, for V and W vector spaces, then you have a basis for the tensor product, which is taking the pure tensors like this. Okay. That's a very powerful thing. Okay. Now let me also make another comment that depending on who you've learned these things from, some mathematicians like to be very explicit and compute with bases and compute with matrices and things like this, and actually the theory was developed like this, and tensors originally were considered like three-dimensional things that look like matrices. As mathematics became more modern, as people like to say, people like to work less with bases and more abstractly. And so there are some people that believe that if you don't have to choose a basis, then you should prove things without choosing a basis. It's a more canonical way of doing things. And that's fine. That's a good point of view that we will certainly take sometimes. But I want to make clear to you that in the kinds of Hopf algebras that we are going to study, that are very combinatorial in nature, very often you have a natural basis in your hands, whether it's permutations or graphs or things like this. And so it's often useful to think about this in terms of basis when you have combinatorics, because the bases are part of the combinatorics. Okay? We'll say more about that. Other comments. If you take V tensor W, that's the same thing as W tensor V. I mean, they're isomorphic in the context of linear spaces or in the context of algebras. Okay. Also, if you take a tensor product like this, it does taking tensor products is associative. Okay, that's not obvious in the, from the outset, but it is true, and that allows us to define something called this, right? So we just take this and we define it to be U tensor V tensor W without parentheses. Okay? And in general, you can define the tensor product of k things, and it doesn't matter how you parenthesize, you're going to get the same object. Okay. Another one is that if you have something like this, a direct sum tensor something, that is the same thing as you can have the distributive property. Okay. Plus V tensor W. And again, these things are true whether you think about it in k vector spaces or in k algebras. Okay. So these are some observations that you might find useful, and so you can feel free to use them. Another observation that I want to make is that very often we have been interested in computing, in constructing a homomorphism from a tensor product to something. And the way we do it is by constructing a bilinear map. Okay? So how do you construct bilinear maps? Well, it's actually very easy if you have bases. So let me just make another comment here that if you want to define a function from, let's say, u times v to w bilinear, okay, or what's equivalent a linear function like this, okay. So here u, v, and w are vector spaces. One way of doing it is just choose bases for these guys. Okay, so choose a basis. U sub I and V sub j for U and V. And then you can define f of ui vj to be whatever you want. Define f of ui comma vj arbitrarily. You better make sure that it's in w. That's the only way that it's not arbitrary, but otherwise you can choose it to be anything. And then you just extend bilinearly. Okay? So this is just like defining linear maps by defining them on a basis. Okay. And you can easily write a formula for f of uv in terms of these things, and I did it on the notes. But I should let you do it. Try it yourselves, and then if you get stuck, look at the notes. Okay. So these are some tools to work with tensor products. Okay. Any questions about any of these things? I don't know why erasers are designed to erase black ink only. So maybe I'll try to stick to black as much as possible. Maybe another example of a tensor product that's important . Another example is what's called extension of scalars. Okay. What is extension of scalars? What you do is let's say that you have an algebra over a field K. If A is a K algebra, And one good example is that if you have something like an R algebra. So for example, the polynomial ring in over the reals. And you say, actually, I want more scalars. For example, I want to introduce the complex numbers. Okay. So let's say that you have some bigger field, some field extension. Then how can I somehow introduce the bigger set of scalars to A? So the standard trick to do this actually is a tensor product. So all you have to do is take the tensor product of A and L, and this is going to be an L algebra. Now there's a couple of things to say here, so let's be a little bit careful. Okay? I'm taking a tensor product of A and L. Now whenever you have more than one field, you want to be very careful about which field you're talking about. Because A was a K algebra, if I want to take a tensor product, it should probably be a tensor product of K algebras. And so I need to put a little K here to indicate that this is a tensor product of K algebras. Okay? Tensor product of K algebras. Okay? Is there something that worries you about this construction? We're taking a tensor product of K algebras, and A is a K algebra, but L is some bigger field. So is there any reasonable way to think of L as a K algebra? Because again, we have to be in the correct category. If we're going to be taking tensor products of K algebras, this needs to be a K algebra, which it is, and this needs to be a K algebra. So is L a K algebra? Well, if you remember what a K algebra is, one of the ways of thinking about it is that it's something that, yeah, it's like a ring that contains K. And it's, being a field, you're a ring, and it contains K. And so that means that this really is a K algebra. Okay? It might not look at it at first, but it is a K algebra. And so if I have two K algebras, I can take the tensor product. And I'm going to get, in principle, a K algebra. And so maybe I shouldn't say is, again, I'm being imprecise, because if I take the tensor product of two K algebras, I get a K algebra, but this can be made into, can be regarded as an L algebra, because it is a ring, we know how to multiply things here, and it contains L now, right? Because you have the representatives 1 times L. Okay? So it contains L, and therefore you can regard it as an L algebra. Okay? So in particular, one thing that we did here, in the example that I just erased, we took the real polynomials and we tensored with the complex numbers over the reals. Okay? And we saw that this is C of x as R algebras. But the point is that you can take this thing now and regard it not as a real algebra, but as a complex algebra. And you know how to do that because these are complex polynomials, and so you will have no issue regarding this as a C algebra. Okay? And the point is that this can always be done. Okay? So this is also a C algebra. Okay? And so this is one standard trick that we have. If you have a K algebra and you feel like you don't have enough scalars and you want to have more scalars, then this is how you introduce them. Okay. So that's all that I wanted to say in my review of tensor products. Okay? It's kind of a quick review. But I know some of you told me that you hadn't seen tensor products, or maybe if you had seen them, you had never worked with them, and so at least I wanted to kind of go through these things. And I know you're getting plenty of practice in the homework, right? So, okay. So let's move on to something a little bit different now. We're going to do something that's a little bit more combinatorial now. I should tell you that my hope for this class is that we do a lot of abstraction and a lot of concrete things. So from abstract constructions to concrete examples. Okay? And so one thing that I would like to discuss is how does a combinatorialist enter the picture here? So far, this has all been very algebraic, and combinatorialists like to count things, right? So, I mean, that's a very rough description of what a combinatorialist does, but you could say that one of the things that combinatorialists do is count things. So what is there to count here in a K-algebra? Well, K-algebras, if you wanted to count the elements, they tend to be infinite sets. But whenever a combinatorialist sees a vector space, the combinatorialist will want to know what the dimension is, if possible. Okay? And so, for example, what is the dimension of the... And so let's talk about how you measuring how big algebras are. Now let's start with a simple example. Here's an algebra over K. Would you say this is a big algebra or a small algebra? And you have to choose. Small? Small. What is the dimension of this algebra? So small, okay. It looks small. What is the dimension? What do we mean by dimension? Well, a K-algebra is a K vector space. And that's the way in which we mean dimension. It's the dimension as a vector space. What is the basis of this thing? 1, x, x squared, x cubed, etc. It's an infinite basis, and so this is countably infinite. Okay? Countably infinite. Okay? I don't know, maybe if you're a set theorist, you think this is small, but a combinatorialist does not think this is small. And maybe we can find a better way of measuring this, okay? At least better for our purposes. And so what we're going to do is we're going to say, actually, this is not so big because it only has one generator of degree 1, one generator of degree 0, degree 1, etc. In each degree, you have one generator, okay? And so actually, we more want to say, in each degree, the dimension is 1, and therefore, it's small. So what do we mean by degree? Well, here it's clear because we know what degree is. But how do we talk about degree in a K-algebra? Well, we cannot always do that, but we can sometimes do that. And so I'm going to make a definition that a K-algebra, say a K-algebra A is graded if there is a decomposition, if it has a decomposition as a direct sum of A0, A1, A2, etc. Okay? And so what we're thinking in the back of our minds here, so is that AI is what? In this case, we're saying, okay, the polynomial ring is, as a vector space, it's the constants plus the multiples of x plus the multiples of x squared and so on. And we're thinking that AI is consists of the things of pure degree I, homogeneous of degree I. So we call this the homogeneous component of degree I. The elements are homogeneous elements of degree I. That's what we call them. Okay. What else should we demand here? Or do you think this should be already called a graded algebra? Huh? Multiplication has not entered the picture, right? So far, this is just talking about vector spaces, and this is a direct sum of vector spaces. And this is an algebra that we should be paying attention to the multiplication. So what should the multiplication satisfy? So I think I see what you mean when you go like this. So if you take something of degree I, multiply by something of degree j, it should land in degree I plus j. Right? Such that if you multiply things in ai by things in aj, that should always be in plus j, right? For all I and j. Okay. So that's what we mean by a graded algebra. Okay. And so the idea is degree I, degree j gives you degree I plus j. And then we're going to define the Hilbert series of A is this. It's a formal series. It's a function of Q. And what you do is that you take the sum of the different graded pieces. From d equals 0 to infinity, you take the dimension of AD times Q to the d. Okay? So we take the dimension of each piece and we make a formal series out of it. Yeah?
You make the same thing with the sub-algebras of each level? Maybe like in the homework. You construct an ideal and like turn this ideal in every dimension.
Mm-hmm. So your question is, if we decide to mod out by an ideal, can we make sense of this being also a graded thing
Also
and
the Hilbert,
also get a Hilbert series? That's a great question, and I'm going to answer it in a second. Let's talk about some easier examples first, and then we'll get to that one, which is a very important example. But let's do easy examples. So examples. Let's say that A is k of x. Okay, as we just discussed, we can write this as the direct sum from d equals 0 to infinity of the things of degree AD. Mm-hmm. Sorry, the things of degree D. What are the things of degree D? Well, they are just this, right? So any constant times x to the d. Okay. Do you guys have a question? Or? Okay. So in degree d, the only thing you have is the multiples of x to the d. Right? Now, what is the dimension of this thing? As a k vector space, well, you know, they're just the multiples of x to the d, and so you have a single basis element x to the d. So the dimension is 1. Okay. And therefore, the Hilbert series is just the sum from d equals 0 to infinity of 1 times q to the d. Now, I hope that nobody wants to leave the answer like this. You have this, you know what this is, so we just write it like this, right? It's the geometric series. If you're an analyst, you might be getting a little antsy and uncomfortable now. And there's two ways that we can deal with that. One, you can say, well, you can regard this as a function of a complex variable, and as long as the norm of this is less than 1, this is true. But an algebraist or a combinatorialist might just want to say, you know what, I'm just going to regard this as an element of the ring of formal power series. And so this has no meaning as a function of Q. We're just thinking of this as, people like to describe it as as a clothesline, a colgar la ropa. So you put the first number is A1, the second number is A2, the third number is A3, and you're not evaluating anything. It's just the elements are clotheslines, and then there's a rule for multiplying them. And all of this means is that if you multiply this times 1 minus q, you get 1. And that's a formal identity in the ring of formal power series. And yeah, so in both senses that identity is true. Okay. Okay, let's do an example that's a little bit more interesting. B, let's let it be the polynomial ring in n variables. Okay. So, well, polynomials have notions of degree. So we can do this where B sub d is the span of what? It's the span of the monomials of degree d, right? So x1 to the a1 up to xn to the an, such that all of the ai's are greater than or equal to 0, and they sum to d. Okay? So now if we want to find the Hilbert series, we need to figure out the dimension of this thing. Okay? And now if you like combinatorics, this is where you might, like, okay, you know, maybe I like this, maybe I know how to do this. What we need to do is figure out, I mean, this is the basis, right? These things are linearly independent from each other, and you just have to count them. So how many ways are there to find n numbers that add up to d and are all greater than or equal to 0, and they're integers? You guys remember? Do you know? Have you seen this before? Maybe? So I see maybe you have some ideas of how to do this. Combinatorics is not a prerequisite for this class, and so we're gonna do this real quick. Okay. So we wanna count the number of AIs. So these guys are natural numbers, and they add up to d. Okay. En Colombia, 0 es natural, ¿cierto? A veces. Para mí 0 es natural. 0 is a natural number, okay? Not everybody agrees, but I agree with myself. You guys agree with me? At least that's what we need to count, okay? So the trick we do is that we say, let's add 1 to each one of these numbers, okay? So I'm going to just define bi to be ai plus 1, okay? So now I need to count the numbers b1 up to bn such that the bi's are now positive integers, and they add up to more, right? They need to add, to each one of these we added 1, and so if these guys added up to d, these guys add up to n plus d. Okay. This is a bijection, right, between these and these. You just take these, add 1 to them, and you get these. Take these, they're bigger than 0, so you can subtract 1 from them, and you get these. Okay, and then there's several tricks to do this, but one trick is the following. You say, take n plus d once, and I want to find n numbers that add up to n plus d, so just introduce n minus 1 plus signs. and minus 1 plus signs. Just in some of the spaces put a plus sign. And so what are you going to get? You're going to get the sum n plus d written as 3 plus 2 plus 2 plus 3 plus 2. Had you seen this trick? You like it? It's nice, no? I think it's a nice trick. It's a bijection, okay? Given numbers like this, you can figure out where to put the plus signs. And given the plus signs, you know where to put what the BIs are. So how many choices are there? Well, how many plus signs do I need to put? N minus 1. And how many places do I have to put them? N plus d minus 1, because I have n plus d once, and I have 1 minus for the number of caps. Okay. So that's the answer. The dimension is n plus d minus 1. Choose. Remember that a choose b is the same as a choose a minus b. So instead of writing this, I'm going to write this. And they're the same thing. Okay? Let me be a little bit trickier than this. How much is minus n choose d? Minus n choose d is, well, you know the formula for x choose d. X minus 1, x minus 2, up to x minus d plus 1, divided by d factorial, right? Let me take out all the minus signs. There are d terms here, so I get minus 1 to the d times n plus 1, up to n plus d minus 1 over d factorial. But if you look at this is precisely n plus d minus 1, choose d. The formula for this is n plus d minus 1, n plus d minus 2, up to n. Okay? You should probably do this yourself slowly to make sure I'm not lying to you. You probably kind of believe me, and you have to check that I didn't make any small mistakes. This formula is true. And so instead of writing it like this, I'm going to write it like this. Minus 1 to the d times minus n, choose d. Okay? So this is just some combinatorial trickery. I'm not doing anything too radical here. But now let's take the Hilbert series of this thing, and you will understand why I'm doing this. I get the sum from d equals 0 to infinity of the dimension of the dth piece. So I get minus 1 to the d minus n choose d, and then times q to the d. Okay? Now, we would like to simplify this. And the first thing you'll notice is that minus 1 to the d times q to the d is minus q to the d. So let me take this and just forget this here and put it in here. And now, do you recognize this series? Especially if I put x here and if I put alpha here, the sum of alpha choose d, x to the d. This is exactly the binomial theorem. And this is exactly the binomial expansion of 1 minus q to the minus n. Or 1 over 1 minus q to the n. Okay? And so again, you see that we just get a really nice, beautiful, simple formula for the Hilbert series. And if n is equal to 1, if I only have one variable, I get this. Yeah? Okay. Any other questions about this? Okay. Here?
Yeah, you put m plus d minus 1, choose d.
Uh-huh.
Why is that d?
So here what I'm using is that a plus b choose a is the same as a plus b choose b. Where here this is a and this is b. And the reason for this is that if you want to choose a elements out of a set of a plus b, you have to not choose the other b. And so that's why these two things are the same. Okay. And I hope this is beginning to give you some ideas of what the homework will look like a little bit. You might end up having to play with series similar to these ones. Okay. Let's do another example, one that so in your homework, the tensor algebra, which we define as the sum from d equals 0 to infinity of the d-th tensor product of v with itself. Okay? So this is a direct sum, and we define tv to be equal to this direct sum. But we need to make sure that this is graded. We need to make sure that the multiplication property holds. But the thing is that if you take a tensor of length d and you multiply by a tensor of length e in the tensor algebra, you're going to get a tensor of length d plus e. And so that's why this is graded. And so naturally, your job now is to find a basis and count it. So homework. Find a basis for each one of these things and count them. And find the generating function. And now let me address Sebastian's question. What if I want to consider the other ones, like the symmetric algebra, where we mod out by the ideal generated by U tensor V. In San Francisco, they told me that my U's look like V's. So V tensor W minus W tensor V. Or the exterior algebra, which is this. So if I'm asking you to compute the Hilbert series, I must be implying that these are graded, right? And so here's a general fact that you can use, that if A is a graded algebra, and now I want to consider an ideal I. Okay. Fill in the blank. Then A mod I is a graded algebra as well. Yeah?
En estos ejercicios lo primero que pues como es un espacio vectorial en principio cuando uno hacía el cociente era como quitarle el subespacio, pues quitar como toda esa dimensión. Pues claro, al comienzo era como restando dimensiones, pero eso era un
Pero falta.
despelote bravísimo, eso era muy difícil.
Yeah, so because we're talking about dimensions of vector spaces, you might be tempted to think that this is the vector space generated by these things. In which case it would only live in dimension 2. And so you want to say, okay, well, what, we're talking about the ideal here, so you can take any of these generators and multiply it on the left by anything, on the right by anything, and that's a bigger ideal.
O sea, como que cuadrándolo dentro de cada dimensión, o sea, que si eran tantos, quitando todos esos, pues la cuenta era muy difícil. Necesito combinatorics.
Sí. Yeah, I mean, and one point is that even if finding the Hilbert series of A is easy, finding the series of a quotient can be very, very difficult. It depends very delicately on the combinatorics of the ideal. I think that's your point, that the combinatorics of this and the combinatorics of this make these problems rather different from the other one. There's some similarities, but they're different. What should I put here?
Two-sided.
Two-sided. Generally, every ideal we're going to consider is two-sided because things are not commutative here. So
Graded.
So graded meaning, you see the thing is, for example, if I take k of x, y, and I mod out by x minus y squared, then what is the degree of x? Well, the degree of x, you would think it would be 1, but here x is equal to y squared. So is it degree 1 or degree 2? You can't really know. And the trouble is that this is not a homogeneous thing. Okay? And so what you need is a homogeneous thing here. A homogeneous ideal. But here these are homogeneous, right? These are generated by things of degree 2 in both cases. So when I say homogeneous ideal, I mean generated by homogeneous elements. Okay. Then A mod I is a graded algebra with grading inherited from A. Okay. In other words, if I mod out by x squared minus y squared, then you're going to know what the degree of x squared and of y squared is. It just comes from the grading here. Okay. And this is a lemma that it's not too difficult to check, and it justifies why these things really are graded rings and why they really have a Hilbert series. Which I think when you start playing with them, you realize that they're graded. You understand what the grading means, just the length of the tensors that are involved. But this kind of puts the definitions more precisely. Okay. Okay. So that's what I was planning to say about graded algebras. Did you have any questions about that? Okay. So this is supposed to be a class about Hopf algebras, and so far we spent most of the time talking about algebras. And I should tell you that we're going to say much more about algebras, but I think we should start getting a little bit used to some new things that appear in Hopf algebra theory that do not have to do with algebras. Okay? And so what I want to do now is talk about coalgebras. Okay. So this is a good moment to kind of stop, change mindset. We're going to do something somewhat different. You can consider this part 2 of the class. So we started talking about algebras, now we're going to talk about coalgebras. And I should ask you, has anybody here encountered coalgebras before? Okay. I had never really encountered them until the homework. I had never really encountered them until I learned about Hopf algebras. So let's define what a coalgebra is. Okay. So this definition is going to be, it's kind of long, but I think now this will make some sense to you. So definition: a coalgebra is a k-vector space which we're going to call it C for coalgebra, with linear maps from C to C tensor C and from C to K. And so we call this the coproduct or co-multiplication, and we call this the co-unit. Okay. And this should remind you that the way we define product, we define it to be a map from here to here, and we define the unit to be a map from here to here. This is, remember, product was taking, A tensor A to A, and remember that the unit just told us how to embed the field into the algebra. So this is kind of the same thing, but with the arrows pointing in the other direction. Such that some diagrams commute. Okay. And you might already know what to expect here. All I'm going to do is draw exactly the same diagrams that I drew for algebras, but I'm going to reverse all the arrows and make sure that everything makes sense. Okay? So we had a diagram of associativity for algebras, and you can probably guess what I'm going to call this diagram. This is the diagram of coassociativity. It looks very similar. So we have the same things, same tensors, but now let's see what maps we should put. Delta goes from C to C tensor C. So presumably this should be delta, and this should be delta. Okay? And how do you map C tensor C to C tensor C tensor C? I mean, one thing I should say is that we don't really have a way of mapping this to this. Right? And so what I'm going to do is that I'm going to leave the first C alone and let delta act on the second coordinate. So this map takes the first coordinate and leaves it alone, and takes the second coordinate and applies delta to it. Okay? And here I do the same thing but backwards. So I take the first coordinate and I apply delta to it. So I get these two, and the second coordinate I leave alone. Okay? And I want this to commute. So this is some sort of coassociativity. Okay? And I also have the counitary property, which again, same picture as before. I just take the A's and make them into C's. I reverse all the arrows, and I change the names of the maps. So there we had this, K tensor C, and C tensor K. And let's see what the maps should be. So we talked about how we have a natural isomorphism between these two things. Okay? So we're going to just let that be the natural isomorphism. What do? I take an element C here, and I map it to one tensor C. And that's an isomorphism. From here to here, I apply delta, coproduct. Okay? What should I do from here to here? The most natural thing is, since I have a map that goes from C to K, I'm going to apply it in the first coordinate and leave the second coordinate alone. And here, I'm going to do the opposite. Leave the first coordinate alone and apply the co-unit. Okay. And this is our other property. Okay? So it's same diagrams as before, but the arrows are reversed. And the maps are also reversed. Okay? So do you guys have any questions about this definition before we do some examples? Epimorphism is surjective, right? That's what it means? Yeah. Yeah, so remember that in the context of algebras, we showed that this definition implied that the unit was injective. And so your question is whether now the co-unit is surjective, and I think it's a very natural question. I'm pretty sure the answer is yes. Yeah, it has to be. It has to be because, why does it have to be? So we'll see that there's a little bit of trouble dualizing actually. So we cannot just dualize everything. But you see, what can the image of a map from C to K be? It's either K or 0, right? Because K is a field. So as soon as you hit an element that is not 0, you're going to hit the whole field. I mean, the image has to be an ideal, and the only ideals in a field are the full thing or 0. And so either the co-unit is surjective or it's 0. And if it was 0, then you would not be able to commute here. Because this map is not 0, and if this map is 0, then this map would be 0. So in fact, you're right, and the co-unit is surjective. And I think it's a great question, and this you really should be thinking about this, that whatever things are true about algebras, hopefully you can kind of dualize and say the same thing here. Say the analysis. So let's do some examples. Let's do some examples just to see what kinds of things we're talking about. So for example, when we talked about algebras, one of the first examples of an algebra was the group ring. Given a group, we made a ring out of it. We're going to try to do something similar here. So before we had a group, now we're just going to take a set. And now we're going to make a vector space out of it by just taking formal combinations of this. So this is a free vector space generated by S. So the elements are just formal linear combinations of S. Okay? So now I need maps. I need delta from here to here. Sorry, from here to here. Right? Now, because this map is meant to be linear, that means I can just define it for generators, and that will define it for everybody. So let's take a generator here for, like, for example, little s, and send it somewhere. Okay? Where would you like to send it? What would you do? To what? To 2 copies of S. Okay. And I think you were suggesting something different? The same thing? Okay. It might be that something different also works. But so for example, we already talked about how you might want to do 1 tensor S plus S tensor 1. Maybe that works, maybe that doesn't work. You have to check. Okay? But we're going to check it for this guy. So now what should our co-unit be? We need to take our coalgebra to the field, And again, we do it on generators. So what should we do here? What's the most natural thing to do? You're going to send it to the field. Probably you're going to send it either to 0 or to 1, which are the only two special elements in a field. And you just have a set. And you have no reason to expect that some elements of the set are better than the others to send some to 0 or some to 1. Everything seems to be the same. And so the most natural construction would be to send everybody to the same thing, either to 1 or to 0. We already talked about how you don't really want to send everything to 0. So maybe we try sending everything to 1. Hopefully this works. Okay. So we need to check. We need to check that this works. So let's check coassociativity. Okay. So I'm going to start with an element over here and take it around. So let's take an element here. And we're going to show that we get the same thing going over here or over here. Okay. I start here. Let's take a basis element. Again, you can just check in on basis elements. So a basis element here is just going to be one of the elements of my set. Okay. I map it up. What do I get? I apply delta, which just does S tensor S. Okay. And I map it to the left. So what does that do? It takes the first copy and leaves it alone. S tensor. And it applies delta to the second copy. S tensor S. Okay. And this looks like it's going to work. Right? If you go the other way, you get S tensor S. And then when you go up, you're going to get that you apply delta to the first S, which gives you S tensor S. And you leave the other one alone. You get this. And these two are equal to each other. Okay? And so that's why coassociativity holds. Now let's see why co-unit holds. Let's start with an element down here. We map it up. And so it goes to S tensor S. Now let's map it over here. So what does that do? The first guy gets sent by the co-unit to 1. And the second guy gets left alone, 1 tensor S. Okay? But we talked about how the natural isomorphism sends S to 1 tensor S. Okay? So this commutes as well. And you do the same thing on the other side, and you see that it also commutes. So you see that this is a very easy way of constructing a lot of coalgebras. And you see that where to construct an algebra, we needed to have a group. Here we don't need any structure on S. We just need it to be any set. Okay. Example 2. This is more interesting. So example 2 is that we take a poset. Is everybody happy with posets? Partially ordered set? You have all seen them, or? So what is a partially ordered set? Something like, I'm just going to draw it. You have something like this. So it's a set with a partial order relation where this is less than this is less than this. The order is, if A is less than B and B is less than C, then A is less than C. So on. Okay. So P is a poset, and I'm going to consider I to be the set of intervals x comma y. Okay. So what is an interval? Well, I like to draw my posets like this. Okay. Here's a poset. Maybe it keeps going like this. I don't know. And then an interval is that you say, okay, take x, take y, and look at all the elements in between. So the things that are bigger than x, bigger than or equal to x, less than or equal to y. Okay, so that's the interval from x to y. I look at all the intervals. And I'm going to let C be the linear combinations of intervals. Okay? So an element of the coalgebra is just going to be a sum of intervals. This interval plus this plus 2 times this interval, etc. Okay. Let me make sure that we're completely clear. So when I write xy, I mean the element z of the poset such that z is between x and y. Okay? Okay. So I'm going to define delta from C to C tensor C. And what I'm going to do is I'm going to take a basis element. Okay? So a basis element is an interval, right? And I'm going to send it to somewhere, something in C tensor C. There's different things that I could try here. And I want to do something that uses the poset. Okay? And what I'm going to do is the following thing. I'm going to take the sum over the things in the interval of xz tensor zy. Okay. So the way to think about this is that you have, here's x, here's y, and then you're looking at all the different ways of picking an element in between and doing this tensor this. Okay. How many elements are you going to have here? As many as there are between x and y. Okay. And this is clearly something that depends on the poset very heavily, right? Now, let's actually consider okay, so the counit, it needs to map a basis element to something. Okay. And again, it seems natural that you should map things to either 0 or 1. Now, would you say that every interval is the same here, or are there reasons to distinguish some intervals from others? I mean, here is not like a set, right? In a set, if I give you a set and I don't tell you anything about the set, everything is the same. I would say there's two kinds of intervals. Interesting intervals and uninteresting intervals. So what is an uninteresting interval? Well, it depends on your notion of interesting, but there's intervals from x to x, which are pretty boring intervals. And they're different from the other ones that are from x to something that's really bigger than x. Okay? And so let's use the counit to distinguish between those two kinds. So I'm going to say that this goes to 1 if x is equal to y, and to 0 if x is less than y. Okay. Why do I do it like this and not the other way? Because I prepared class and I saw that if I did it the other way, I would not get a coalgebra. It would not satisfy the axioms. But we will see that this satisfies the axioms. Okay. Let's check that this is actually a coalgebra. So this is more fun. And maybe
You should, like, in the poset you have elements that are not like comparable between.
in a poset you can have elements that are not comparable, like these two.
So you should define zeros with the
But the thing is that if I have an interval, then in an interval x is always less than or equal to y.
okay.
So it's already built into this. The basis elements are pairs x, y, where x is less than y, less than or equal to y. I kind of wrote formulas here. So if you want formulas, read the notes, but I'm going to give you a proof by picture. Okay? So let's do this. Okay, I'm going to check coassociativity. Okay? Let us take a basis element here. Okay, so here's the poset, and our basis element is some interval here. Okay? Who does this get mapped to? The poset is still there. X and y are still there. But the coproduct maps me to things that look like this times this. Okay. So this is just a schematic thing to say sum over all z's, this tensor this. Okay. Now let's see who this maps to. So here's x, here's y. Okay, now what happens to So what happens when I apply the coproduct? When I apply this map. I apply the identity tensor, the coproduct. So what I'm going to do is that in the first coordinate, remember this is this tensor this, and the first coordinate I have to leave it alone. So I'm going to draw in orange the result. I wish I had a more different color, but I don't. So here I just get this in orange. That's what this identity does. It leaves the first component alone. What does this do? It takes the top half and splits it into two pieces. Okay. It just goes over all the maybe W's here. And it does that. And so what I get is the sum of the coproducts of this tensor, this tensor, this. Okay. And maybe you can kind of see why this is going to be coassociative. What happens if we go in the other direction? Let me go over here. P, x and y. And let me draw in purple the result. Here I'm applying the same map, so the result is the same, right? So I get this. And now let me apply the map that goes up. Okay. So this looks like this, and then I still have this for reference, and I still have this for reference. But now let's see what the map does. So going from here to here, I take my first coordinate, I apply delta to it. So I need to take my first coordinate, which is xz, and split it up in all the possible ways. Something like this times something like this, where this is now my new w, let's say. And my second coordinate, I have to leave it alone. I apply the identity. And so I get this. Okay. So this is still z, and this is still x and y. Okay? And so do you see why these two things are the same? Basically, the result of going either like this and this, or like this and this, is that you're going to take, well, let me maybe, I'm going to take x, y, and it's going to map to, in formulas, it's going to map to the sum over x is less than or equal to a less than or equal to b less than or equal to y XA tensor AB tensor BY. Okay. So it's just a way of splitting the interval into 3 jumps. And it doesn't matter if you split first this way or first this way. Okay. So that's what it means to be coassociative here. Okay. Does that make sense? And so then you begin to see that actually this begins to get pretty combinatorial. And actually, one way of thinking about coproducts is that there are very useful ways of understanding how you take a combinatorial object and you split it into 2 combinatorial objects. Okay. I'll let you check the co-unitary property so you can have fun with these pictures also. I have a proof written. Actually, I didn't write the proof for co-unit. So here's a nice exercise is to check the co-unitary property. And it's a nice exercise. You see that there's also a nice combinatorial picture to go with it. Okay. So these are two examples of coalgebras. And just to conclude my class today, I want to go back to your point, which I think is very important, which is that this looks just like a dual thing to algebras. It looks like they're kind of the same theory, but the other way around. And so I want to make that more precise. Let's introduce duality here. So recall that if you have a vector space, V is a K vector space, then we have something called the dual vector space, right? The dual vector space is denoted V star. It's also denoted as HOM K VK. It's just the linear functions on V. Linear. And for some reason, whenever we talk about linear functions, we like to call them functionals. So linear functionals on V. So this is a definition. Linear functions from V to the base field. You can see that these two things are isomorphic as vector spaces. They have the same dimension, but it's good to always keep track of which is which one is vectors, which one is functionals. But as in any notion of duality, you should have that the dual of the dual should be V. And that's something that you should check if you're not familiar with it. So we have a notion of duality for vector spaces. And so what is the statement that you would make about algebras and coalgebras? What would be your guess about algebras and coalgebras? For example, if C is a coalgebra, meaning it's a vector space, but it has additional structure. It's a vector space with maps that satisfy these axioms that I just erased. Then it looks a lot like an algebra, and what would be the most optimistic guess as to what is happening? The dual, if we're lucky, the dual is an algebra. In some natural way inherited from C. And dually, if A is an algebra, then the dual should be a coalgebra. Okay. And this would be called duality between algebra and coalgebras. Okay? The problem is that it's not true, but the good news is that it's almost true. This is true. This is not true. It's a little bit surprising. But here, this is true if your algebra is finite dimensional. But somehow if you're not finite dimensional, then that result is not true. Which I find kind of intriguing. And we will see next time why this is true and what this condition of being finite dimensional is about. But this says that the similarity between algebras and coalgebras is not just aesthetic, it's not just that it looks similar. There really is a content to that duality.